Okay, so we are to basically our last lesson in chapter 1, and that's lesson 1.7, the distributive property. And in this lesson, we're going to use the distributive property to help us simplify expressions. Now, this property is going to help us in the next chapter to solve equations. So this is another one of those topics where you're going to see a lot of the things in this class, they build on each other. So I'm going to describe the property with some examples here. And we're just using A, B, and C as real numbers. Now this won't make a ton of sense. I'm going to use examples with actual numbers instead of variables. Okay, just variables. I'm going to use a combination of variables and letters. But the first few are just showing if I have a number, let's just say number 5. And it's multiplied by a quantity in parentheses like x plus 6. All I do is I distribute that 5. So I multiply it by x, I multiply it by 6. So that becomes 5x. 5 times x is 5x plus 30, because 5 times 6 is 30. That's it. For the next example, it's just flip-flopped. I'm going to use the same numbers to show that in multiplication, the order doesn't matter. I still multiply by both terms inside the parentheses. Okay, so that's how we use the distributive property, and that's just across addition. If I do the distributive property across subtraction, it's basically the same thing, except we have to really pay attention to, in subtraction, the order does matter. Okay, so when I multiply this next one, I'll use different numbers. 9 times z minus 3. And then I just multiply 9 by z, that's 9z. And I multiply 9 by negative 3, which is negative 27. So it's just understanding that in this case, 9z has to come first, 27 has to come second. And I treat that as like negative 27 because I'm subtracting 27. And again, it's just if I have the number being multiplied behind or after the parentheses, I still multiply 9 by z and then 9 by 3. So it's still 9z minus 27. Okay. So we'll get into some examples about on this, and I mean, it's just applying this. And I should have given you some time to write that. We're going to take some time to write these expressions in simplified form, and just give you a different exposure to different numbers. So for example 1, simplified form of each expression, 3 times the quantity x plus 8, I do 3 times x is 3x, 3 times 8 is 24, so 3x plus 24. For part B, I'd multiply negative 7 by 5b, that's negative 35b, and I multiply negative 7 by negative 4. I treat that like negative 4, so this is positive 28. Okay. So if you want, you can try this number 1, parts A and B, they're kind of like independent practice. So I'm going to like stop talking for a second, give you a chance to pause the video, all right, and work through these. And then when you're ready, after a few seconds, the answers will flash on the screen. You can move ahead, all right? So moving to example 2, finding a sum or difference that's equal to a quantity divided by just a number. It's just basically distributing, kind of like you're distributing a fraction, because this expression is the same as me doing 1/5 times 7x plus 2. So if I did that distribution, all this would be is 7x over 5 plus 2 over 5. And that's it. And that's simplified. So really, you're just writing each term over this number in the denominator, in the bottom of the fraction. So same process for that number 1 at the top. If you want to try these, I'll give you a few seconds to pause the video. Once you're done working through them, you can check my answers and you can move forward. All right. So moving ahead, we're going to use the multiplication property of -1, and it's a very simple concept, but it's understanding that if I have just a negative sign multiplied by a quantity in parentheses, I treat this as -1, okay? So it's like I'm distributing -1 through that expression. So when I do that, I multiply -1 by 2y, that just becomes -2y. I multiply -1 by -3x, that becomes positive 3x. So the main thing I want to get across with that is that multiplying by -1 does not just make things negative. Multiplying by -1 changes the sign of a number or a term, okay? So when I talk about terms, I'm going to talk about that in a second. 2y in this expression is a term. -3x I call a term. And I say -3x to, in my head, understand that that is subtracting 3x. So a useful way you can use the distributive property kind of in everyday life is to do some mental math. So in example 4, talks about Julia, and she commutes to work on a train 4 times a week. A round-trip ticket costs $7.25, and finding the weekly cost using mental math. So I want you to try to do this without a calculator. But if I'm looking at this, a way I look at this is I break it apart in my head to do this mental math. I would do 4 times, and I know 7.25 is 7 plus 25 cents. So I can use distribution to do 2 separate multiplication problems and then combine them together. So just the dollar cost, the cost of just the $7 4 times is $28. And then I know I can do 4 times a quarter. 4 quarters is $1, so that's plus 1. So this is really a total cost of $29. So it's breaking apart numbers in a way that makes sense so you can do some mental math. So sometimes you do that. You don't realize you're doing it, but in your head, you're kind of using the distributive property to do some mental math at certain times, right? So I thought that was an interesting, maybe useful example to show you. So our last example today covers something we come back to a little bit later in the year, but is still something we do cover in solving equations. And it talks about terms and like terms. So I'm going to read this out and go through example 5. A term is a number, a variable, or the product of a number and a variable or variables. Like terms have the same variable factors. So in this expression, 5x squared is a term, 3xy is a term, -2xy is a term, 19 is a term. And I'm going to highlight the like terms in this expression. 3xy and -2xy. Those are like terms because they have the same exact variables with the same exact powers on them. So 3xy, 2xy, I'm just looking at the x and the y. If either of those x's or y's were raised to different powers, those wouldn't be like terms. The variables have to be identical for the terms to be like terms. So in example 5, part A, looking at 8x squared plus 2x squared, those are like terms because they both have x and x is squared in both terms. So all this becomes, we just add the numbers on the front. We add 8 plus 2, so that's 10x squared, okay? So in part B, I want to just highlight some of the like terms. So in part B, 5x, -3x, those are like terms. -3, +4 are like terms. So when I simplify this, I'm going to do 5x plus -3x is 2x. I'm going to do -3 plus 4, which is +1. And then 6y doesn't have any like terms, so it remains 6y. So that's a nice little example to show different types of like terms. And there's certain times, if there are no like terms for a term, that term just stays the same. It does not change. So again, at the end, a chance for you to do a little bit of independent practice. Again, I'm going to pause for 5 seconds to allow you to pause the video. And then my answers will flash on the screen. You can compare them with yours and then move on to the practice I have assigned for you in Google Classroom.